All right, let's take a look at question number 5. So let's see here. Um, f of x is 2x squared minus 6x plus 4, and g of x is 4 cosine 1/4 pi x. And it says let R be the region bounded by the graphs of f and g, shown in the figure below above. Find the area of R. Okay, so R is a region bounded by these two curves. So if you look at f of x, this is a quadratic function that has upward facing concavity. Okay, so if you look at these two functions, the function that has upward facing concavity is a function on the bottom. Okay, so this is f of x, which is 2x squared minus 6x plus 4. And then the function on the top is your cosine function with a x with a stretched out amplitude period, and then the amplitude has also been increased by a factor of 4. So g of x is equal to 4 cosine 1 over 4 pi x. Alright, so you have to be really careful here. In most textbooks, f is normally the function on the top and g is the function on the bottom. But you notice that the rules have been reversed here. So you don't want to stick with the function with the names of the functions. You want to stick with the order. Okay? So f could be the top and g could be the bottom, or the reverse also. Alright, so you have to be careful with that. Now, let's go ahead and write down the expression for the area. So for A, the area of a region bounded by two curves is basically the integral from A to B. In this case, we are going to be dissecting our region using vertical rectangles. Now, how do we know to use vertical rectangles or along the x-axis? Well, if you look at the two functions, they are in terms of x, so that's a giveaway. So we need to find rectangles of infinitely small widths. Let's call them dx, and then we're going to integrate, find the infinite sum of all the vertical rectangles that we have. All right, so this would be integral from a to b of f of x on the top minus f of x on the bottom. Okay, so well, let's use g for the second function so we don't get this confused. F of x minus g of x. So this is basically the general formula you see in a lot of textbooks. F on the top minus g of x on the bottom. So in this scenario, our area is going to be the integral. We are integrating from, let's write down the coordinates of our points. This is 0, 4. And then this point right here is 2, 0. We are just going along the x's. So from x equals 0, we're going from 0 to 2 of the function on the top. What's the function on the top? In this problem, it is g of x. Okay? Minus the function on the bottom. In this case, it's f of x. Alright, and then dx. So let's go ahead and evaluate input our function into these two functions. So we're going to have the integral from 0 to 2 of g of x is 4 cosine 1 over 4 pi x. Okay, minus f of x is 2x squared minus 6x plus 4. Alright, now let's find the antiderivative here. Before I do that, let me quickly review some integration rules with you. The integral of, let's say, cosine ax, okay, dx. Do you know what that is? That is going to be sine ax. Using the u substitution, you're going to end up with the coefficient as a denominator. That's a shortcut you can use. Okay, sine ax over a. That's the integral of this. Okay, now let's say we're integrating e to the ax, for example. Using the same shortcut, it's simply going to be e to the ax over a. Remember, when differentiating this, you multiply by that coefficient, right? But when you're integrating, you just divide by it. So it's a shortcut to, simplify the u substitution process. If you forget this formula, you can use u substitution and you'll be just fine. All right. So let's go ahead and integrate this expression. So it's going to be factor out the 4. Antiderivative of cosine is sine 1 over 4 pi x divided by the coefficient of x. So again, divided by the coefficient of x, which is 1 over 4 pi. Let's just use pi over 4. Okay, so that's the antiderivative of the first term minus term by term integration here. The antiderivative of that expression is going to be 2x to the third, 2x to the third over 3 minus 3x squared. This is 6x. You're going to differentiate. If you integrate this, it's going to be 6x squared over 2. 2 goes into 6 3 times, plus 4x. Okay? And then we're evaluating this from 0 to 2. You might want to panic and say, oh, this would take me a long time to evaluate. But the beauty of this expression is, if you evaluate this function at 0, sine of 0 is 0, so this entire expression becomes 0, and this entire expression becomes 0 also. So what we're doing in essence is evaluating this function at 2, okay? So let's go ahead and do that. I'll multiply 4 by the reciprocal of the denominator, so it's going to be 16 over pi, and then sine. If I put 2 in here, you have 2 pi over 4, which is pi over 2, sine of pi over 2. And then minus, put 2 here. We're going to have 2 to the third power, which is 8 times 2 is 16. 16 over 3 minus 2 squared is 4 times 3 is 12, plus 4 times 2 is 8. Okay, and then sine pi over 2, we know that that's 1, so we're going to have 16 over pi, and then to evaluate this, put this over 1, put that over 1, times this by 3 top and bottom, and this one also by 3. Okay, so you're going to have 24 plus 24 minus 36 minus 16. Okay, and we can simply work that out. All right, so we have, let's see, we have 16 minus 36 plus 24. If you combine these two, you get 40 minus 36. Let's see what we have here, which is 4. So we have a minus here, so it's negative 16. Is 16 over pi minus 4. Minus 4 over 3. Okay, so there goes your final answer. All right, let's take a look at the B part. The B part we're to set up. It says, write but do not evaluate an integral expression that gives you the volume of a solid generated when r is rotated about the line y equals 4. So you notice we are rotating about a line that's above both functions. So I have a detailed tutorial explaining how to calculate volume of solids of revolution. So you should check that tutorial out to understand how I'm setting up the formula that I'm about to use. All right. So let's take a look at question B. So for B, we're going to be using the formula. The general formula is basically B equals the integral from A to B of pi times the outer radius square, which gives you the area of the outer disk, minus pi times the inner radius square, which gives you the area of the inner disk. So if you subtract the 2, you'll be left with the area of the washer, dx. Okay? Alright, so in this situation, the outer radius is going to be what you get when you subtract this function from f of x. Okay, so let's set it up. We're going to have, this is going to be, the volume is going to be factor out of pi. We're still integrating left to right, so we're going from 0 to 2. And it's going to be 4, that's the axis of rotation, minus f of x. Okay, so this will give us the outer radius, but we have to square it. So the outer radius square minus 4 again, minus the inner function, which is g of x relative to y equals 4. That one's square. Okay, dx. Remember, we're just to set it up. Okay, so this is a setup using the function. So finally, we're going to have pi times the integral from 0 to 2 of This squiggly bracket 4 minus f of x, which is 2x squared minus 6x plus 4. Don't forget to square it. Radius square minus 4 minus g of x, which is 4 cosine pi over 4x. That's quantity square equals your integrand dx. And that's the expression for the volume when the region is rotated about the line y equals 4. Let me just give you a visualization as to what the function is going to look like. This is not going to be a great sketch, but I'll just try my best to show you. So if you have that function, that region, looking something like this, have that region, and then we have an axis of rotation right here. So you just spin it around. So what's going to happen is that this region gets reflected straight up, something like this, like that, and then it's basically, imagine it spinning around, okay, and then you have a solid where this is the cross-sectional area, and then you have a washer, you know, so that washer is basically what we added from 0 all the way to 2. The infinite sum of the volume of that washer is what gives us this integral expression. All right, let's shift our attention to the C part. We have the following situation. I go over this on the other tutorial too, but I'm just going to use the formula here. So if it's too abstract for you, you want to go back and look at that tutorial on volumes of solids of revolution and cross sections. All right, so it says the region R is the base of a solid. For this solid, each cross section perpendicular to the x-axis is a square. Write down but do not evaluate an integral expression that gives the volume of the solid. All right, so let's go ahead and I want to give you the visual of what the situation looks like first before I create the formula, okay? So let me rotate my x-axis, slant it a little bit. I'm going to rotate my y-axis. So there goes my y-axis, and that means the function is going to be laying on its side. So let's say this is the function that we're dealing with, something like that. That's the quadratic function, and then we have the trig function like that. Okay, let me draw the trig function again. So there goes the quadratic function, and let me fix the quadratic function. It goes down a little bit. This is just a rough sketch, pardon me. And then there goes your trig function. Okay, so what's happening is the cross section is basically this region right here. That cross section is the base of a square. Okay, so basically we have a square right here. So we have a square. Alright, so you have the square looking like that. So what you have is an infinite number of squares just like this, stacked on top of these two functions right there. Okay, so the area, the formula for finding the volume of the resultant solid, we have a whole bunch of squares stacked up on the solid like that, is going to be the area from A to B of the area of a face of one of the shapes, in this case a square, dx. Alright, so this is a square, so we need to find the area of this square. Okay, let's say the side is s and s. We know what the area of a square is, right? It's s squared. What is s? S is the distance between two functions. The function on the top, remember, is g of x, and the function on the bottom is f of x. So our s is basically g of x minus f of x squared, right? Because that's a side length. That's what the side length measures. So our volume, sorry, I forgot to put the v there. Our volume in this scenario is going to be the integral from 0 to 2 of 0 to 2 of g of x minus f of x. That's the length of the side of the square for the area dx. Okay, now let's put in our input function. So we have the integral from 0 to 2 of let's see, of g of x, which is 4 cosine pi over 4x, minus f of x, which is 2x squared minus 6x plus 4. All right, and then that square dx. Okay, so that's basically the volume of the resulting solid. Okay, so that's that. All right, let's take a look at question number 6. We're given a differential equation. It says consider the differential equation dy dx equals e to the y times 3x squared minus 6x. Let y equals f of be equal to f of x. Be the particular solution to the differential equation that passes through 1, 0. Write equation for the line tangent to the graph of f at 1, 0. Use the tangent line to approximate f of 1.2. So how do you write equation of a line? We can use the point slope form, y minus y1, this is the a part, equals m x minus x1, okay, where the line goes through the point x1, y1. So in this case, we have the point 1, 0, so that tells us automatically that x1 is 1 and y1 is 0. So the only ingredient we need to generate the equation of our line is a slope m at x equals 1. So m at x equals 1 is the same thing as the derivative dy dx of this implicit function at the point 1 comma 0. Okay, or I can write it as, let me change my notation a little bit. I can write it as the derivative where xy is equal to 1 comma 0. Same thing as what I wrote before, but this tells you that x is 1 and y is 0. So what does that mean? It means that anywhere we have y in this equation, we put in 0. And anywhere we have x, we put in 1. Okay? So that's going to leave us with e to the 0 times 3 times x squared becomes 1 squared minus 6 times 1. Close that. E to the 0 is just 1. 3 minus 6, which is equal to negative 3. Now we have the slope, so let's write down the equation of our line. So we're going to have y minus y1, y1 is 0, equals the slope, negative 3, times x minus x1, which is 1. Get y by itself, that implies that y is equal to negative 3 times x minus 1, and that's the equation of your line. Okay, well, we are asked to approximate f of 1.2, so how do we do that? Well, f of x is equal to negative 3 times x minus 1. This is the equation of our tangent line, so we can use it to approximate the slope nearby, all right? So f of 1.2 is going to be approximately negative 3 times 1.2 minus 1. Okay, so this becomes, if we subtract the quantity in the parentheses, you have negative 3 times 0.2, multiply that out, you have negative 0.6. Okay, so that's that. All right, let's take a look at the b part. The b part, we are to solve the differential equation with the initial condition f of 1 equals 0. So for the b part, we have dy dx equals e to the y times 3x squared minus 6x. So we can solve this by separation of variables. What does that mean? We have all the y's on one side and the x's on the other side. So we have dy, divide both sides by e to the y. So we have dy over e to the y equals, and multiply those sides by dx, you have 3x squared minus 6x dx. Okay, so I hope this makes sense. All I just did is, this is like we're solving an algebraic equation, right? Multiply this both sides by e to the y dx and e to the y dx, right? So in this side, e to the y's cancel out, and over there, let's switch it around. So this becomes dx over e to the y. Multiply both sides of the equation by the same thing, dx over e to the y. So the dx is canceled out here, so that's why you have dy over e to the y equals this expression here. All right, so to get rid of the dy's, we have to integrate both sides of our equation. So we're going to find the antiderivative of 1 over e to the y dy equals the integral of 3x squared minus 6x dx. Okay? All right, so um, this integral right here, you have to be really careful when evaluating it, all right? So we can write this integral as e to the negative y dy, and then we can use the power rule for integrals to evaluate this. This is pretty easy to evaluate, so this is going to be 3x to the third over 3, which just comes out to x to the third, minus 6x squared over 2, which is 3x, plus c. Alright? And then to evaluate this integral, remember the formula we went over earlier. If you have an integral of e to the ax dx, that's simply going to be e to the ax. Using the use substitution, you end up with e to the ax over a. Okay? In this case, a is negative 1, so this integral is going to become e to the negative y divided by negative 1, so we just put a negative here, okay, equals x to the third minus 3x plus c. Now, this other c here, we can just add it to this c, okay? It's just some constant that we are going to find right now. Now, how do we find that constant? We know that f of 1 is equal to 0, so that's our y, and this is our x. So we're going to plug it in here to find out what the constant c is. So we're going to have, what are we going to have? We're going to have, this becomes negative e to the negative 0 equals 1 to the third minus 3, supposed to be square, forget that, minus 3 times 1 square plus c. Okay? So let's get c by itself. To get c by itself, this entire expression, negative, is just e to the 0 is going to become negative 1. This negativity stays behind. E to the 0 is just negative 1 equals 1 minus 3 plus c. All right, and then when you get c by itself, you're going to end up with c equals negative 2 plus 3. Negative 2 plus 3 is simply 1. Okay, so that's what c is. So now we can find the particular solution of our differential equation. So we have, let's box this. We're going to have, plug it into this piece right here and get y by itself. So by doing that, we're going to have negative e to the negative y equals x to the third minus 3x squared plus 1. Okay? Now, if we want to get y by itself, we can multiply everything by negative 1. So we have e to the negative y equals negative x to the third plus 3x squared minus 1. And then to get rid of this e, we just take the natural logarithm of both sides. So this implies that the natural logarithm of e to the negative y is equal to the natural logarithm of negative x to the third plus 3x squared minus 1. So these two cancel out, so we have negative y equals the natural logarithm of negative x to the third plus 3x squared minus 1. Divide both sides by negative 1, you have y equals negative the natural logarithm of negative x to the third plus 3x squared minus 1. Alright, so there goes your final answer. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to our channel for updates to other cool clips such as this. And please post in comments to let us know what you think about this presentation. More clips can be found on mathperserve.com/calculus. Thanks again for watching and have a wonderful day.